Ever wonder how scientists can talk about the size of an atom or how bankers can map out interest over decades, all without filling up entire pages with zeros? Well, they use a kind of secret language. It's a super powerful tool that makes the impossibly huge and the unimaginably tiny suddenly make sense. So let's dive in and decode this secret language of exponents together. Okay, let's just start with a challenge. Imagine you have to write down the number 1 with 25 zeros after it. I mean, you could start writing 1, 0, 0, 0, 0, but honestly, you probably lose count, run out of paper, and get really, really bored. There's got to be a better way, right? Well, there is. And a solution is that secret code we've been talking about, exponents. They are the ultimate mathematical shortcut. A clean, super elegant way to handle numbers that are just way too big or way too small to deal with otherwise. So what exactly are they? Let's jump in and break down the basic blueprint. And hey, don't worry about a bunch of crazy formulas just yet. At their heart, exponents are built on a really simple idea. Okay, so here's the deal. An exponent is just an instruction. You've got the big number on the bottom, that's your base, and the little number up top, that's the exponent. All that little exponent is telling you is how many times to multiply the base number by itself. Seriously, that's it. Let's look at a classic example. 2 to the power of 3. So our base number is 2. The exponent, that little 3 up top, tells us to multiply that base by itself 3 times. So we get 2 times 2 times 2, which of course equals 8. See? Simple. Here's a cool way to think about it. An exponent is basically a copy machine for multiplication. The base is the original thing you want to copy, and the exponent just tells the machine how many copies to make. All right, now that we've got the basic idea down, let's see how this builds into some really powerful shortcuts. And look, these aren't just random rules you have to memorize for a test. They're actually just really clever patterns, and once you see how they work, it all just clicks. All right, let's try something. What happens when you need to multiply two numbers that are already using exponents, like 2 squared times 2 cubed? Now, you could figure out each one out separately and then multiply them, but there's a way cooler shortcut. The trick here is to just write it all out. Let's expand it to see what's actually happening under the hood. 2 squared is just 2 times 2, and 2 cubed is just 2 times 2 times 2. Now, let's put it all together. And right there, that's the aha moment. If you just count them up, we've got 5 2s all multiplied together. So how do we write that with an exponent? Easy. It's just 2 to the power of 5. And that brings us to the first big rule. When you're multiplying powers that have the same base number, you don't have to do all that expanding. You just add the exponents. So 2 plus 3 gives you 5. This rule is a total game changer, a huge time saver. Okay, so we've handled the huge numbers. But what about the other way? What about things that are ridiculously small, microscopic even? For that, we need to dive into the world of negative exponents. Just take a look at this table here. As we go down the list of powers, from 3 cubed to 3 squared to 3 to the first, do you see the pattern? What's happening to the result every single time we take a step down? 27 becomes 9. 9 becomes 3. We're dividing by 3 each time. So, following that logic, what comes next? If we just follow the pattern, 3 divided by 3 is 1. And see? This isn't just some weird rule someone made up. It's the logical next step. And it's true for any base number. Anything to the power of 0 is 1. Period. Okay, so what if we go one more step? 1 divided by 3 is 1/3. So a negative exponent isn't scary. It's just another instruction. It means divide instead of multiply. It basically just flips the number into a fraction. 3 to the power of -1 is simply 1/3. All right, so we now have tools for the incredibly big and the incredibly small. Let's put it all together and see how scientists use this to talk about, well, the entire cosmos. This is where something called scientific notation comes in. Okay, look at this number. That's the distance to the nearest star, Proxima Centauri, in miles. It's a beast, right? It's a nightmare to try and write that out, or heaven forbid, use it in a calculation. You're just asking to make a mistake counting all those zeros. But now, watch this. That monster number on the left and this clean, simple little thing on the right, they're the exact same number. That's the power of scientific notation. Instantly, it's 1,000 times easier to read, to compare, and to work with. And the best part is, the recipe for doing this is super simple. All you do is take your big number and kind of smush it down so it's a number between 1 and 10. In this case, 2.469. Then you just count how many spots you had to move the decimal point. That count, that becomes your exponent on the 10. That's it. Okay, so let's tie this all together. We've gone through the rules, the shortcuts, but why does any of this really matter? It's because exponents are quite literally the language of scale. They're how we make sense of the universe. Think about this. With those negative exponents we just talked about, we can easily write down the diameter of a single proton. That little -15 tells us we're in a world so tiny, our brains can't even really picture it. And then, in the very next breath, using the exact same tool, we can write down the diameter of the entire observable universe. That power of 26 is just mind-boggling. It's incredible. The same simple idea describes the absolute smallest thing we know and the absolute biggest thing we know. And that is the real magic of this secret language. This isn't just for astronomers and physicists. It's the engine behind how money grows with compound interest. It's how we measure earthquakes on the Richter scale. It's how computer memory grows. From the smallest particle to the largest expanse, exponents give us the power to make sense of it all, to measure it, to actually understand it. The only question left is, what will you use them to measure?